I'm Dr. Michael Wood of the Physics Department and Pre-Engineering Program here at Canisius College. And I wanted to talk to you a little bit about a concept called total internal reflection. So I've been actually spending a lot of time at home lately, and I've noticed when I peer out the window that if I look at the window in my house and I look outside, I can see what's outside, but I can also see my reflection inside the window pane. So I wonder, why is it I can see light coming through the glass, but I also see light that's reflected off the glass in the window? And it actually comes about from a concept called Snell's law. So Snell's law, written down in a mathematical form, says the index of refraction of one medium times the sine of the angle is equal to the index of refraction of another medium times the sine of its angle. So what do all these numbers and letters mean? Well, what it means is if I look at glass and I consider the air on the inside of my house, and if I have a light ray which is now coming in at some angle, theta 1, inside the air, and then it hits the surface of the glass, and then the angle here of the light as it goes through the glass is measured with theta 2. So theta 1 is the angle of the ray of light measured from the perpendicular of the surface, and theta 2 is the angle of the light traveling through the glass, also measured by the perpendicular. And with that equation, I can then calculate exactly where the ray of light is going to be going in the glass. But it also takes into account these things I've called the index of refraction. So air has an index of refraction, which I'll call N1, and glass has an index of refraction, which I'll call N2. And these indices of refraction actually describe the behavior of light inside that material. So the index of refraction, refraction being a fancy word for how much light bends inside of a medium, the index of refraction is defined as the speed of light in a vacuum divided by the speed of light in a material. Now, light slows down when it goes into a material, so that speed of light in a material, like glass or plastic or water, is always going to be less than the speed of light that you have in a vacuum or air. Air is pretty thin, so we can call it the speed of light in air or the speed of light in vacuum. Um, but so that index refraction is a ratio of how fast light is moving with respect to the speed of light in a vacuum. And so, and in the index in glass is going to be much bigger than the index of refraction in air, because the speed of light in glass is much slower than the speed of light in air. And that's why the light bends. The light bends is because it's moving slower in that material. And so in order not to go faster than the speed of light in a vacuum, the light has to bend. It has to get out of the way. So the interesting thing is, if I take this equation, which I've written right here with the name of Snell's law, and consider a case where the index of refraction where the light is starting is bigger than the index of refraction of where it's going. So imagine I have a denser material like glass, and as compared to something like air, then if I put that into my equation, what I have is a bigger number times the sine of its angle is equal to a smaller number times the sine of its angle. And let's just say, for the sake of argument, that I get all the way to the point where the angle is 90 degrees. Well, everybody knows that the sine of 90 degrees is 1, so that means my equation becomes index of refraction in the material, glass, times the angle at which it's hitting the glass, or hitting the surface, is just now equal to the index of refraction of that other material. In this case, I called it air. So in that case, I can now solve for the sign of this, which is now the ratio of the index of refraction in one material divided by the index of refraction of the other material. And I said it had to be the special case where n1 is greater than n2, because if n2 is greater than n1, I would get a ratio which is bigger than 1. And again, everybody knows the sine of any angle cannot be greater than 1. The answer to any sine problem is always somewhere between -1 and 1. But the interesting thing is that this is now called the critical angle. And it's called the critical angle because that's the angle at which light is now going to bounce right off and just reflect back into that material. And so what I get is light coming in, hitting at some critical angle, and then bouncing right back out again. And I get no light shining through that material. So all I get is reflection off of something as simple as glass acting like a mirror, but it's still transparent, but it gives us a reflection. And to kind of show that a little more, I'm going to pull up this simulation where the simulation shows a laser beam which is now bouncing off of the interface. So I've got air up here in the white space, I've got glass down here in this kind of purple space, and you can see that the light is going to be reflected. Some of the light's reflected off the surface, and some of the light goes right through the glass, so we can see it on the other side. But if I switch these around and make this light going from glass into air, now I can get that critical angle. And so I can see here, light is escaping the glass and going out into the air, but eventually I'm going to reach an angle, a critical angle, where all of that light gets reflected and no more light goes out of the glass. The light doesn't escape. All the light is totally reflected inside that material. So I hope you've enjoyed this brief lecture on a really cool topic like total internal reflection and Snell's law.